to talk about an interesting circuit that looks at resistors, capacitors, and a voltage-dependent current source. And we're going to look at the structure up here. And I just kind of want to think about it for a couple minutes, and then I want to talk about the implications of this structure after I kind of talk about how you would analyze it. Again, we have some interesting parameters we'll work with, and we'll talk and sort of plug those numbers in as we go. So if I wanted to solve this, pretty much in this case, the simplest thing is to do KCL at one node. I mean, pretty much, or two nodes, I pretty much have this node here at V1 and this node here at V out. That basically gives me this sort of core equation. Looking at the first one, I can kind of do some simplifications, which gives me kind of a typical relationship between V in, V out, and V1. So that works out pretty smoothly. I can sort of look at the second part, and that also I can start to pull apart equations from there by both grouping the V1 and V out terms, the V1 to this side, the V out to the other side, and you can kind of see where those terms show up. Now, assuming that your GM is, effectively much bigger than 1 over R2, so that would mean that whatever this term is much bigger than R2. Is this true? Well, we have R2 is 100 kiloohms, and GM is 1 over 300 ohms. So you're like, okay, yeah, that's probably pretty reasonable, and something to consider in that design. Then, you can get rid of that first term, gets rid of that messy sort of negative sign. You're like, oh, I wonder what that's going to do. It works out, but it's not something to be too worried about here. And you end up getting this equation, which then allows me to then start to pull all the pieces together, and I get this interesting transfer function that V out is a sort of GMR2, which kind of, again, means, okay, that's now bigger than 1, which is not a shocking thing given how we're putting this together. 1 plus SCR2, so I get a time constant here to work with. And so it looks like effectively I have this sort of integration between V out and V1. So it allows me to at least figure out what's going on there. So there's an integration going on, and then when I plug all this back into V out over V1, I can sort of rearrange the terms I'm going to get, which is an R2 over R1. And, this is V out for V in, is an R2 over R1, and then I get a term that gives me my timing underneath. 1 plus this additional term, typical for a lot of circuits that have some gain with feedback in it. And then I also get my time constant. And you think, this is interesting. Why is this circuit kind of an interesting circuit? Well, it turns out that how this circuit looks is actually pretty indicative of what this structure for an op-amp circuit often really looks like. Now, we often talk about ideal op-amp where, if I have an output capacitance, it really doesn't do anything because, after all, it's ideal, right? And it just has a perfect voltage source and there's nothing to worry about. In reality, real op-amps have frequency responses. And the reason they have frequency responses is that they're actually creating that high gain by a current or a GM or a transconductance element. So voltage to current, so voltage control current source element, that is the core of what's actually being used. And that, coupled with a capacitance, is what you get. Now, this isn't true for all op-amps. Some you will have different characteristics, but you will find that this will be true for quite a number of structures. And one way or another, you're going to get a similar property out of a lot of different op-amps in practice, which makes it interesting. And in fact, if you actually look at the response then from V1 to V out in an ideal case, what you find is that because it's an integration, it's basically going to be, there's going to be a maximum gain at some point, which is an upper gain level, which might be 100,000, but there's going to be a corner frequency of around 5 hertz. And this is always kind of a surprising thing, and I think the first time that this became really clear that op-amps actually look like this, it was like, oh wait, but this ideal model is only sort of true. But it turns out even with the frequency dependence, it still works out well. And maybe a better way to look at it is I've got this region over 6 orders of magnitude, 5, 6 orders of magnitude typically, where it acts like it just drops linearly with frequency. It was called an integrator. And so what you're really doing with an op-amp often is making an ideal integrator. And sort of understanding that turns out to be really cool, right? So this GM over SC, and we kind of could see this in this calculation for V out to V1, GM over SC at the certain point. And you could kind of just talk about this. And with the parameters we have, this is the number we would have gotten over 500 kilohertz over F. 500 kilohertz, by the way, connects to something that we would call the unity gain frequency. It's kind of cool, actually. And so, of course, what we get here is a gain of 10. We actually end up getting the corner at a factor of 10 up from that, which is 50 kilohertz up in this region. So it actually works out pretty well. I like this particular problem because it really illustrates a number of the things that you often see with actual practical structures. Including the fact that with resistive feedback I get a nice gain of 10 until the amplifier kicks in, and then it just follows down accordingly. And so in practice, this is often how you think about op amps in practice. Now, there still are ideal op amps, so of course, when you get an ideal op amp, analyze it like an ideal op amp. But there are also times to go, wait, maybe this sort of comes out in that actually many different circuit problems may actually be disguised as actually an op amp problem, but with a little more realistic features for those op amps.